which is approximately 6.97 parkers per second.
Something like
6.97 parkers per second. This velocity. Mass of 255 grams. Rests on a oh yeah. Vertical spring. I forgot to include that in the problem statement. With constant 41 newtons per meter, the mass is compressed an additional 13 centimeters, then released. The question is, what is the speed of the mass when it loses contact with the spring? Now, the question is, when will this mass lose contact with the spring? Yeah, so we got a spring, mass is sitting there. Then we smush it down and let go. So if the mass is attached to a spring, where do you think it's going to lose contact with the spring? Equilibrium point. Why? Just
logically.
Because once it passes the equilibrium point, the spring is going to start to snap back. Does that make sense? So then it will lose contact. Yeah. So in this case, I'm going to use the other version of our equation. Initial energy equals final energy, because I want to. You can use either. What kind or kinds of energy do we have to begin with? Spring potential energy. Gravitational, do we? So the displacement we're given is relative to the equilibrium position of the mass spring system, and therefore we can ignore gravitational potential energy and only use spring potential energy. That's what we derived the other day when we talked about the vertical spring. So we can just say 1/2 kx squared. And then when it loses contact with the spring, what kind of energy does it have? Just kinetic. Halves go bye-bye. And then some quick algebra gives us this. And then we can plug in numbers, correctly converting units as we go.
I got the number 1 today.
What does this have to do with number 1? So then, I mean, the spring potential energy formula is there, but I got 1.65 meters per second. I want to remind you again that it's a good idea to practice solving things algebraically before you plug in numbers, because on the AP exam, a lot of times you'll have to do things algebraically with no numbers. Yep. All right, what is the maximum height the mass reaches? Well, first off, what is this going to be relative to? Equilibrium of the mass spring system, because that's the only reference point we're given. So, again, we can say, what kind of energy are we going to wind up with then? What kind of energy are we going to end up with at the maximum height? What kind? Just gravitational potential. It won't be touching the spring anymore.
Oh, it's not like tape. It's just
rest.
Oh.
It's not say is attached. Okay, and what kind of energy do we start with? Yeah, 1/2 K x naught squared. Actually, you could plug in 1/2 mv squared too, and it doesn't matter because they're equal. Yeah. So then, this maximum height is equal to k x naught squared over 2mg, and we can plug in numbers from there. .139 meters above equilibrium of the mass spring system. On the AP exam or on a test, like the problem will be stated in such a way that like y equals 0 is here, and then you can just write y equals whatever. Ooh, here's a good one. See if you can set this one up. Now, how is this different than the previous one? Sure, so it's kind of the reverse, but how else? What else is different? Relaxed spring. So where is this 15 centimeters relative to? Equilibrium of what? Of just the spring, not of the mass spring system. So if we've got equilibrium of just the spring, that means we're going to need to include both spring and gravitational potential energies. So see if you can set this up. Think about it. What kind of energy do we have to begin with? What kind of energy do we end up with? Did you say gravitational energy down? Energy is a scalar, dude. It doesn't have direction. You okay, David?
Yeah.
Are you sick?
What?
Are you sick?
No. David? No.
Are you lying to me?
I'm David. No, actually not sick.
Huh?
I'm hungry. No, you're David.
Wow. Wow. I've never heard such witty dialogue in all my years as a teacher. Wake up, Ian Jen.
Wow. Because no, this position energy, right? They drop, and there's spring energy at the bottom. And then you add the position energy.
Well, the previous one we did, you mean? Because of this. So the whole point of this derivation was to show that if we take our potential energy 0 to be at the equilibrium position of the mass spring system, we can treat it as though there's only spring potential energy. Yeah. But this is not from the equilibrium of the mass spring system. I don't know. So Yoonjung, what kind of energy do we start with? Think about it. There are 3 possibilities. We have kinetic energy, gravitational potential, spring potential. Is the mass moving at the beginning? Is the mass compressing or stretching the spring at the beginning?
Oh, yeah.
Is the mass stretching or compressing the spring at the beginning? Read the problem. What is the spring doing initially? Read the problem. What is the spring doing initially? What does it say? Yunjung, read the first sentence aloud. So what's the spring doing? Shh. What was that? Do you need to read it again? It's relaxed. So what does that mean? The spring is it stretching or compressing? The spring is at its equilibrium position. So is there spring potential energy? Guys, cut it out. No. Okay. Is there gravitational potential energy? Are we at some height? So initially we just have gravitational potential energy. At the end, what kind of energy do we have, Alberta? We do have spring potential energy. What kinds of potential energy are there? And? So what? Okay. Both of these are potential energy of the mass, kind of. Well, technically, gravitational potential energy is the potential energy of the mass Earth system, and this is the potential energy of the mass spring system.
So if it's at spring compressed, then would gravitational potential have a negative value?
Right. So this H final will be a negative value.
The whole gravitational potential.
Yeah, this will be a negative. Yeah. And then we say the mass is coming to rest again. So there's no kinetic energy final. As far as this, so if we're setting, what's the best place to set our zero in this case? I think that's the easiest to think about. You could do it when you're compressed too, but then you'd have to move this over here. Yeah, so this is our 0. Okay. And we know that this is going to be compressed. So we know the final height will be below that. So there are two different ways you can deal with this term. You can make it negative, and then you can just assume that the height is going to be below and make it negative, or you can just leave it, and then you'll get a negative value for the answer. It doesn't actually matter. Okay. So what do we put in over here? Mass is 0.255. G, of course, is 9.8. What should I put in for H naught? Nope. You moved your decimal too much.